Welcome to Noah Science. In this episode, we explore one of the deepest questions in modern cosmology. What if anything existed before the Big Bang? Was it really nothing? Or are there hidden traces of a universe that came before our own? If you enjoy thoughtful science-based explorations like this, please remember to like the video, subscribe to Noah Science, and share it with someone who loves space and big ideas. Your support helps this channel grow and lets us keep making calm and depth journeys through the universe. Thank you for watching, and now let's begin. In modern cosmology, the story of the universe begins with an event that current theory calls the Big Bang. According to this picture, about 13.8 billion years ago, the observable universe is compressed into an extremely hot, dense state and then begins to expand. Space itself stretches, carrying matter and radiation with it. This framework is not a casual idea. It is built from several independent lines of evidence that point to a common origin in the distant past. Galaxies are observed to be receding from one another, with those farther away moving away faster, which suggests that space is expanding. The universe is filled with a faint background glow in the microwave range, which fits the description of cooled radiation from an early hot phase. The amounts of light chemical elements such as hydrogen and helium match the predictions of nuclear reactions in a young, dense cosmos. Taken together, these clues support a picture in which the universe has a finite age and a hot beginning, rather than an eternal, unchanging past. In this standard view, time has a special role. The equations that describe large-scale gravity, the equations of general relativity, allow one to follow the history of the universe backward. As the clock is run in reverse, galaxies draw closer. The average density of matter rises and the temperature increases. At each earlier stage, the universe is more compact and more energetic. In the mathematics, this trend continues until at a certain idealized limit, the density and temperature would become infinite. That limit is called a singularity. It sits at what is labeled time zero, the formal starting point of the expansion. In the simplified models used in textbooks, all of space and all of time beyond that point are said to emerge from this singular beginning. However, this formal beginning is not the same as a physically understood state. When a calculation yields infinities, it usually signals that a theory is being pushed beyond its domain of validity. The singularity at the Big Bang is widely interpreted in this way, not as a real point where density literally becomes infinite, but as a marker where current theory can no longer be trusted. At densities that high, the quantum behavior of gravity should become important. Yet general relativity, as successful as it is on large scales, does not include quantum effects. A more complete description, often called a theory of quantum gravity, would be needed to describe what really happens at such extreme conditions. Until such a theory is secure, the status of the Big Bang as an actual beginning or as a transition from some earlier state remains open. This is why cosmologists sometimes say that the Big Bang marks the beginning of the observable universe rather than the absolute beginning of everything. Observations and established theory describe with growing clarity what happens from very early times onward. There is a period of rapid expansion called inflation that likely takes place in the first tiny fraction of a second after the formal singularity. There is a hot, dense plasma of particles, radiation, and fields. There is a sequence of cooling phases in which the basic ingredients of matter take shape. All of this can be studied with a mixture of theoretical models and astronomical measurements. But when the line is traced all the way back to the singularity itself, the tools that otherwise work so well effectively fall silent. The question of what if anything exists before this horizon in time therefore sits at a delicate boundary. On one side, there is a successful, deeply tested description of an expanding universe. On the other side, there is mathematical uncertainty and physical speculation. The sample of events that can be observed always belongs to the part of the story that unfolds after the hot beginning, because any light or particles that carry information must travel through that later universe to arrive at detectives today. As far as direct signals are concerned, the early fireball acts as an obscuring wall. Anything that might have occurred before it is hidden behind the fact that space is once opaque and then violently expanding. In practice, this does not stop the question from arising. Human curiosity turns naturally toward origins and endings and the Big Bang as the earliest well-defined point in the history of the universe becomes a focal point for that curiosity. Researchers differ in how they interpret the meaning of time zero. Some emphasize that within classical general relativity time has no extension beyond the singularity. So it is reasonable to say that time itself begins there. Others note that general relativity is known to be incomplete in the extreme conditions of the early universe. So any statement about an absolute beginning may be premature. Both perspectives agree on one key fact. With present tools, the universe cannot be reconstructed to a state earlier than a very early cutoff, sometimes referred to in theoretical work as the Planck time at which quantum effects should dominate. This situation gives the Big Bang model a curious character. On the one hand, it is one of the most successful theories in science, able to account for a vast range of observations with a simple set of assumptions. On the other hand, it carries within it a built-in limit, a place where its own equations predict their breakdown. That limit is not a decorative feature. It is rooted in the very structure of the equations that define the theory. The consequence is that the question of what happened before the Big Bang, if that question is meaningful at all, cannot be answered by simply pushing the same equations further. It requires either a new framework or a reinterpretation of what is meant by time and beginning. In this way, the Big Bang functions less as a solved origin and more as a horizon. It is a surface of ignorance that advances slowly as theory and observation improve, but still leaves a region beyond that remains inaccessible. Over the past century, the horizon has moved inward from a vague notion of a past explosion to a precisely timed hot phase with specific properties. Future progress in understanding quantum gravity or in reading more subtle fingerprints from the earliest accessible moments may move it further still. Yet for now, the formal singularity at time zero stands as a reminder that the current story of the universe starts at a point that is sharply drawn but not fully understood. That tension between clarity and incompleteness is the opening through which ideas about what might have come before begin to enter. To move beyond the abstract idea of a hot beginning and into the tangible details of the early universe, cosmology turns to a particular form of light that fills all of space today. This light is not bright to human eyes. It is a faint glow in the microwave range with a temperature only a few degrees above absolute zero. Yet it carries a record of the universe as it is when it first becomes transparent. In the standard picture, there is a long early period during which the cosmos is a hot, dense plasma of particles and radiation. Electrons and atomic nuclei move freely and scatter light continuously. Under these conditions, photons do not travel far before interacting, and space behaves like an opaque fog. As the universe expands, this plasma cools. Eventually, about a few 100,000 years after the beginning of the hot phase, the average energy becomes low enough that electrons can bind to nuclei to form neutral atoms. This stage, often called recombination, transforms the behavior of light. Once electrons are mostly locked inside atoms, photons no longer scatter as frequently and space becomes transparent. The radiation that streams out at that moment continues to travel almost unhindered across the expanding universe. Over billions of years, the stretching of space shifts its wavelength from visible and infrared bands down into the microwave region. Today, that radiation is observed as the cosmic microwave background, a nearly uniform bath of microwave light arriving from all directions. The importance of this background lies in the fact that it preserves a snapshot of the universe at the time when it last interacts strongly with matter. By measuring its properties with sensitive radio instruments and space telescopes, scientists effectively gain access to an image of the cosmos when it is only a small fraction of its present age. Early observations reveal that this background has almost the same temperature across the entire sky, which already supports the idea that the young universe is very uniform on large scales. More detailed measurements, however, show that the temperature is not perfectly uniform. There are tiny differences from one direction to another, differences of only a few parts in 100,000. These minute hot and cold spots correspond to slight variations in density and pressure in the primordial plasma. In places where the radiation is a little cooler, the matter density is a little higher, forming the seeds from which galaxies and clusters eventually grow under the influence of gravity. The cosmic microwave background thus acts as a blueprint for later structure encoding the initial conditions that lead to the cosmic web seen today. Over the decades, instruments such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Satellite Map, this fossil light with increasing precision. Each mission refines the picture. The pattern of small temperature variations is analyzed in terms of characteristic angular scales, revealing how matter and radiation interact in the early universe. The data constrain the geometry of space, the total matter content, and the relative amounts of ordinary matter, dark matter, and dark energy. Results consistently indicate that ordinary matter, the kind that forms stars, planets, gas, and familiar objects, accounts for only a small fraction of the total cosmic energy budget. A much larger share is in the form of unseen matter that interacts gravitationally, but not with light, and an even larger fraction appears as a smooth component that drives the overall expansion to accelerate. These conclusions do not arise from a single observation, but the background radiation plays a central role because its statistical properties depend sensitively on these components. In parallel ground-based and high-altitude experiments continue to improve the resolution and sensitivity of cosmic microwave background maps. Arrays of detectors in dry high sites, such as the Atacama Plateau in Chile, probe the sky at multiple frequencies to separate the primordial signal from foreground emissions produced by dust and gas in our own galaxy. One such project, the Atacama Cosmology Telescope, operates for many years to accumulate a deep survey of a large fraction of the sky. By the middle of the decade, its collaborators present detailed maps that complement and extend those made by space missions. These images do more than refine existing measurements. They add new information by resolving finer structures and by capturing the polarization of the background radiation that is the preferred direction of the light waves as they arrive. Polarization arises when the radiation last scatters off electrons in the early plasma, and it carries additional clues about the motion and distribution of matter at that time. When scientists combine temperature and polarization data, they obtain a more complete view of the early universe, including how different regions are moving relative to one another. In effect, these measurements allow researchers not only to see where matter is slightly more or less dense, but also to infer how it is flowing at the moment of last scattering. The increasing clarity of these images produces both reassurance and unease. On the reassuring side, the overall pattern is consistent with the broad outlines of the Big Bang model, combined with an early phase of rapid inflation. Inflation, a hypothesized episode in which space expands extremely rapidly, in a tiny fraction of a second, naturally explains why the background is so uniform on large scales and why the small fluctuations follow a nearly scale-free pattern. The shape of the spectrum of temperature variations, the way their strength changes with angular size, lines up remarkably well with the predictions of simple inflationary models. On the uneasy side, precision also brings out features that are harder to accommodate. Some analyses report that the fluctuations on the very largest angular scales are weaker than expected. Others notice a curious alignment of low-order patterns, sometimes described informally as an axis in the background sky, that seems at odds with the idea that the universe should be statistically the same in all directions. There are hints of hemispherical asymmetries and other anomalies that may be mere statistical accidents or may point to subtle new physics. None of these deviations taken alone is strong enough to overturn the standard picture, but together they form a list of puzzles that remain under discussion. The new high-resolution maps intensify this tension. On one hand, they improve constraints on basic parameters and narrow the room for alternative models. On the other hand, they allow more delicate tests that bring small discrepancies into focus. When the Atacama maps are compared with the Planck data, for example, the overall consistency is good, but certain derived quantities show small shifts. Debates arise over whether these are due to residual foreground contamination, unrecognized systematic effects in the instruments, or genuine signs that the simple model of a flat universe with fixed dark energy and cold dark matter may be incomplete. The community responds with further observations, cross-checks, and joint analyses, but the possibility lingers that the background light may contain more information than is currently understood. There are also more speculative suggestions. Some researchers have proposed that unusual features in the cosmic microwave background, such as ring-like patterns or specific alignments, could be the fossils of processes that reach back before the usual starting point of the Big Bang, perhaps remnants of a prior cosmic cycle or traces of exotic physics operating at energies beyond the reach of current models. These ideas remain controversial and far from established. In many cases, other scientists argue that the claimed patterns are consistent with statistical noise once proper analysis is applied. Yet, the very fact that such possibilities are discussed illustrates how the background radiation functions as a delicate canvas on which both well-supported conclusions and more daring interpretations are drawn. Every new survey that sharpens this picture has the potential either to strengthen the prevailing model or to reveal subtle departures from it. For now, the cosmic microwave background stands as the earliest direct image of the universe. It shows a cosmos that is remarkably smooth, yet not perfectly uniform, already carrying the seeds of all later galaxies. It confirms that the universe passes through a hot, dense phase and expands and cools as theory predicts. At the same time, its finest details leave room for anomalies whose significance is not yet fully clear. In this way, the fossil light of the fireball sits at a crossroads between hard measurement and open question. It anchors the narrative of a universe born in fire and expanding over billions of years while keeping open the possibility that hidden in its faint variations there may be hints of processes that standard history does not yet include. After the cosmic microwave background is released and the universe becomes transparent, there is a long interval during which no new sources of light yet shine. Matter is present everywhere, but it is mostly in the form of neutral hydrogen and helium gas, spread through expanding space. The residual glow of the background radiation gradually cools and fades to longer wavelengths, and there are no stars or galaxies to add fresh illumination. Cosmologists call this period the cosmic dark ages. It begins after recombination, when electrons and nuclei first bind into atoms, and it ends only when the first generation of stars forms and begins to radiate. During this time, gravity works slowly but steadily on the small density variations recorded in the background map. Regions that start out slightly denser than average pull in more matter. Over tens of millions of years, these patches grow into clouds and then into larger halos of gas and dark matter. Because dark matter does not interact with light, it collapses more easily than ordinary gas, forming an invisible skeleton that helps guide the flow of baryonic matter. The gas falls into these potential wells, heats through compression, and eventually, in the densest regions, begins to fragment. Within these fragments, the conditions become suitable for nuclear fusion to ignite, and the first stars are born. These earliest stars, often referred to as population 3 stars, are expected to differ from later generations. They form from pristine gas that contains only hydrogen and helium, produced in the Big Bang. Heavier elements, which astronomers call metals in this context, are absent at first. Theoretical models suggest that without metals to help cool the gas, the characteristic masses of the first stars are higher than those of typical stars today. Many of them may be tens or even hundreds of times the mass of the Sun and live for only a short time before ending in powerful supernova explosions. In doing so, they enrich their surroundings with newly forged elements and help to reionize the surrounding gas, turning neutral atoms back into an ionized state. This sequence marks the end of the Dark Ages and the beginning of what is often called the cosmic dawn, the era in which the universe is lit for the first time by starlight and young galaxies. Observationally studying this distant period is challenging. The light from these early objects travels for more than 13 billion years before reaching telescopes on or near Earth. During that journey, cosmic expansion stretches its wavelengths from ultraviolet and visible bands into the infrared. Dust and gas along the line of sight can alter the signal, and the targets themselves are extremely faint. For many years, the main evidence for the timing of reionization and early star formation comes from indirect probes such as the way distant quasars are absorbed by intervening gas and the imprint of free electrons on the polarization of the cosmic microwave background. These studies indicate that the first luminous sources must appear within the first few 100 million years after the Big Bang, but details remain uncertain. The launch of the James Webb Space Telescope, with its large mirror and instruments optimized for infrared light, transforms this field. Its design is tailored to detect the stretched light from early galaxies, whose emission has been redshifted by the expansion of the universe. Once its instruments are cooled and calibrated, deep surveys begin to reveal galaxies at redshifts that correspond to times when the universe is only a small fraction of its current age. Some of these objects appear to be in place as early as a few 100 million years after the hot beginning. One example that attracts attention is a galaxy identified in the middle of the decade and often referred to by a catalog name that includes the term MOMZ 14. Analysis of its light suggests that it is seen as it was about 280 million years after the Big Bang, when the universe is roughly 2% of its present age. The mere existence of such a galaxy so early in cosmic history is noteworthy. Its brightness implies a substantial rate of star formation, and its spectrum shows hints of a chemical composition that already includes elements heavier than helium, such as nitrogen in notable amounts relative to carbon. This combination suggests that several generations of massive stars may have already lived and died within this young system, enriching the gas from which new stars form. When the Webb telescope surveys a wider area, it finds not only isolated cases like this, but a population of surprisingly bright early galaxies. In some fields, the number of luminous objects at these high redshifts exceeds what standard models of galaxy formation had led researchers to expect. Simulations that start from the small fluctuations seen in the cosmic microwave background evolve dark matter and gas under gravity and include prescriptions for cooling star formation and feedback, generally predict a gradual buildup of massive galaxies over the first billion years. The Webb results indicate that significant stellar masses and high luminosities may have been reached more quickly. This mismatch does not automatically invalidate the standard picture because uncertainties in the models are large. The efficiency with which gas turns into stars, the impact of stellar winds and supernovae on their surroundings, and the role of early black holes can all alter the pace of galaxy assembly. It is possible that early star formation is simply more efficient than had been assumed, or that bursts of star formation are common, briefly making galaxies appear exceptionally bright. Nonetheless, the emerging pattern raises questions. How can the same small initial irregularities that are imprinted in the background radiation produce such prominent systems in such a short time? Does the presence of early heavy elements imply that massive stars form and explode in a way that differs from local expectations? Could there be additional physical ingredients, such as variations in the properties of dark matter or unrecognized heating mechanisms, that speed up structure formation in the young universe. Alongside these broad questions, detailed observations also uncover specific features that are difficult to interpret. Some early galaxies show compact sizes, but very high surface brightness. Others exhibit emission lines that hint at unusual ionizing sources, possibly very hot stars or actively growing black holes. The gas in and around them appears to be in a complex state, partially ionized and turbulent. These characteristics feed back into the larger question of how the transformation from a neutral dark universe to a transparent, ionized, star-filled cosmos proceeds. Each new Webb survey adds data points to the timeline of reionization mapping when and where the fog of neutral hydrogen clears. Instead of a simple uniform transition, the picture that emerges is patchy and extended in time. Islands of reionized gas form around clusters of galaxies and then grow and merge. The pace at which this happens depends sensitively on the abundance and properties of early luminous sources. In this developing narrative, the cosmic dark ages are no longer treated as a static, featureless interval. They become a dynamic stage in which small differences in initial conditions combined with poorly understood processes of gas cooling and star birth determine the onset of cosmic dawn. The first stars and galaxies are not only the origin of familiar elements and structures, they are also strict tests of cosmological models. If they prove to be consistently more massive, more chemically evolved, or more numerous than current theory allows, then the assumptions about the early universe may need revision. For now, the situation remains in flux. Some apparent tensions ease as improved models of star formation and dust and better calibrations of distances and luminosities are applied to the data. Others persist, especially for the most extreme objects. The balance between reassurance and surprise shifts with each new data release. Underneath these technical debates lies a deeper implication. The difficulty of explaining rapid early structure formation within the standard framework invites speculation about whether the initial state of the universe, as encoded in the fluctuations seen in the cosmic microwave background, is fully understood. If not, the anomalies in the timing and properties of the first luminous objects may be indirect hints that the earliest phases of cosmic history, perhaps even aspects of what preceded the usual Big Bang description, leave fingerprints that are only now becoming visible at the edge of observational reach. On scales much larger than individual galaxies, the matter in the universe arranges itself in a pattern that resembles a vast network. Surveys of galaxies in the nearby cosmos, using large telescopes and wide field instruments, reveal that galaxies do not fill space uniformly. They cluster in groups, and clusters stretch along elongated filaments and outline curved sheets that surround immense regions where relatively few galaxies reside. These underdense areas are called cosmic voids. Together, the filament sheets and voids form what is known as the cosmic web. This structure is not an arbitrary pattern. It arises naturally when small early fluctuations in density, like those mapped in the cosmic microwave background, grow under the influence of gravity in an expanding universe. Over billions of years, tiny initial contrasts become amplified. Regions that start out slightly denser pull and matter more strongly and become the seeds of filaments and clusters, while less dense regions empty out. Computer simulations that begin with a set of initial fluctuations consistent with background observations then evolve dark matter and gas according to the laws of gravity and hydrodynamics produce networks of filaments and voids that resemble the observed large-scale distribution of galaxies. In these calculations, dark matter plays a leading role. Because it interacts only weakly with radiation and ordinary matter, it can begin to clump earlier and more efficiently, forming an invisible scaffold. Ordinary gas falls into the potential wells provided by this dark matter skeleton, cools, and eventually forms stars and galaxies along the densest strands. The result is a picture in which the luminous structures observed with telescopes trace the peaks and ridges of a much larger, mostly unseen distribution of matter. Over time, astronomers build three-dimensional maps of the galaxy distribution by measuring not only positions on the sky, but also distances usually inferred from redshifts. These maps confirm that the web-like pattern extends over hundreds of millions of light-years. Individual superclusters of galaxies containing many rich clusters form nodes in this network connected by filaments that can span similar distances. In between lie enormous voids where matter is sparse. The statistical properties of this pattern, such as how clustering strength changes with scale, provide another test of cosmological models. The standard picture, based on a nearly scale-free spectrum of initial fluctuations and a universe dominated by cold dark matter and dark energy, predicts that on sufficiently large scales, the distribution of matter should become homogeneous. This expectation is encoded in an assumption known as the cosmological principle. It states that when averaged over very large distances, the universe should look the same in all directions and at all locations. In practice, this does not mean that there are no structures on large scales, but rather that, beyond a certain characteristic size, the variations should smooth out and no region should be special. Numerical studies suggest that there is an effective upper limit to the size of coherent structures that can form through gravitational growth from the initial conditions provided by the early universe. Above a scale of roughly 1 billion light-years, any apparent pattern is expected to blend into statistical noise. Early large-scale surveys, such as those that first identified walls and filaments stretching hundreds of millions of light-years, already hint at the richness of structure, but still fall comfortably within these expectations. There are impressive features like the Sloan Great Wall that span significant fractions of the surveyed volume, yet the overall distribution remains roughly consistent with the idea that homogeneity is approached on the largest scales probed. As technology advances, new surveys push the mapping of the cosmic web deeper and wider. Multi-object spectrographs on large telescopes measure redshifts for millions of galaxies and quasars. Photometric surveys with wide field cameras chart the sky over vast areas, and weak gravitational lensing measurements, which track how the images of distant galaxies are subtly distorted by intervening mass, offer a way to trace the distribution of dark matter directly. Together, these techniques refine the three-dimensional picture. They show how structures form first on small scales and then merge into larger complexes, how filaments feed gas into clusters, and how voids expand. The growth rate of structure, how quickly clustering develops over time, also reflects the influence of dark energy, because accelerated expansion tends to slow down the formation of new structures by pulling matter apart. In this regime of large-scale structure, tension between observation and theory begins to appear in a different way from that seen in the early universe. while the cosmic microwave background encodes the initial conditions near the hot beginning. The cosmic web records the accumulated outcome of billions of years of evolution. If both are described by the same underlying model with a fixed set of parameters, there should be consistency between what is inferred from the early and late universe. Yet some analyses have found mild disagreements. For example, certain measurements of the clumpiness of matter today obtained from weak lensing surveys seem to suggest slightly less structure than would be expected from extrapolating the background-based model forward in time. Another set of studies examining the abundance of galaxy clusters offers similar hints. These differences are not large, and they remain within the range where unrecognized systematic errors or statistical fluctuations could be responsible. Still, they raise the possibility that either the properties of dark energy or the behavior of gravity on large scales may not be exactly as assumed. Alongside these broad statistical tensions, individual discoveries of especially large or unusual structures further complicate the picture. As new catalogs of quasars and galaxies are compiled, astronomers occasionally identify associations that seem to form patterns on scales approaching or even exceeding the informal upper limit suggested by simulations. Some of these, upon closer examination, turn out to be less significant than first thought, their apparent coherence weakened when more data are added. Others persist as rare but striking features. In such cases, the question becomes how to reconcile their presence with the cosmological principle. If the universe is supposed to be homogeneous on the largest scales, how can there be specific regions that host enormous concentrations or patterns of matter? One response is to treat them as statistical outliers, rare peaks in a random distribution that are unlikely but not impossible. Another is to consider whether the initial conditions or the laws governing structure formation might allow for more extreme features than earlier models assumed. Either way, these discoveries turn the cosmic web from a mere confirmation of expectations into a source of new questions. It still broadly supports the idea of an expanding universe seeded with small initial fluctuations. At the same time, its most extreme examples push against the boundaries of that framework, hinting that there may be additional layers of information encoded in the way matter is arranged on the grandest scales. Among the many structures that make up the cosmic web, a few stand out as particularly large and striking. These immense patterns concentrate attention because they seem to push against the theoretical expectation that beyond a certain scale, the universe should become smooth and statistically uniform. One such feature is a vast arrangement of galaxies and galaxy clusters described in recent years as a ring-like pattern. It is identified in data that map the distribution of distant galaxies along a narrow slice of sky. When their positions in space are reconstructed using redshift distances, they appear to trace out an arc that, when projected, resembles a segment of a gigantic ring. Estimates of its size suggest that it spans roughly 1.3 billion light-years across and stretches along a length of several billion light-years. For comparison, the supercluster that includes the Milky Way occupies a region only a few hundred million light-years in diameter. In the vicinity of this ring-like feature lies another extended arrangement of galaxies known as the Giant Arc, which itself reaches over several billion light-years. Together, These two structures dominate their region of the cosmic web on scales that begin to rival those at which cosmologists expect homogeneity to set in. Their discovery does not immediately overturn the cosmological principle, but it does present a challenge. If such enormous features are possible, how many of them should exist in a universe seeded by small random fluctuations and governed by known physics? And how often should observers like those on Earth expect to find themselves in a region where more than one such structure lies in the same general area of the sky? Statistical arguments suggest that extremely large, coherent structures should be rare. When numerical simulations are used to generate many mock universes with the same basic parameters as those inferred from the cosmic microwave background features, the size of typical superclusters and walls appear frequently, but larger, more coherent patterns become increasingly unlikely. The probability of finding something like a billion light-year scale ring and another gigantic structure nearby depends somewhat on the details of the simulation and the definition of coherence, yet in many analyses it seems low. This raises the possibility that either the initial conditions contain more large-scale power than expected, or that processes operating after the initial phase have enhanced certain modes of structure formation. Observers are cautious. Surveys often have selection effects, and apparent patterns can emerge when data are taken along particular lines of sight that do not represent the full three-dimensional picture. As more redshifts are measured and maps are refined, some candidate structures lose their earlier significance. Others survive scrutiny, their outlines becoming sharper as more galaxies are assigned to them. In this environment, each new report of a large-scale feature triggers both excitement and careful reanalysis. Beyond the Big Ring and the Giant Arc, there are earlier known examples of enormous concentrations, such as the Sloan Great Wall and other named walls and filaments that already stretch standard expectations. These two are rare but not unique. They sit in a catalog of impressive structures that include supercluster complexes, massive quasar groups, and extended walls of galaxies. In each case, part of the scientific effort lies in assessing how likely they are under the prevailing model and whether their existence requires new physics. The gap between what is allowed and what is observed is not straightforward to measure because the concept of a structure itself depends on methods of identification. One can choose different thresholds of density contrast, apply different clustering algorithms, or define coherence in different ways. All of this shapes how often certain kinds of patterns appear. Still, the largest and most regular-looking features are difficult to dismiss as mere artifacts of classification. Their near-geometric appearance, such as the suggestion that the Big Ring might be better described as a spiral or corkscrew-like form winding through space, invites the thought that some organizing principle beyond simple random fluctuations might be at work. Within the standard cosmological framework, one natural mechanism for imprinting large-scale patterns is the phenomenon known as baryon acoustic oscillations. In the early universe, before recombination, fluctuations in the plasma of photons and baryons behave like sound waves compressing and rarefying the fluid on large scales. When the universe becomes neutral and the radiation decouples these waves, leave a preferred scale imprinted in the matter distribution. Later, this shows up as a slight excess probability of finding pairs of galaxies separated by a certain characteristic distance often described as a standard ruler. This effect is indeed observed and serves as an important tool for measuring cosmic expansion. However, the patterns associated with it are statistically subtle and spherical, on average not elongated into huge arcs and rings on the scales suggested by the most extreme structures. For that reason, baryon acoustic oscillations alone do not readily explain the big ring or the giant arc. If these features are genuinely as large and coherent as they appear, they may require either an unusual realization of the random initial field or a modification of the assumptions about that field. Some speculative ideas invoke exotic relics from the earliest moments of the universe. One class of such relics is known as topological defects, which include hypothetical objects called cosmic strings. These are not strings in the everyday sense, but narrow line, like concentrations of energy that could have formed during phase transitions in the early universe when fields settled into new configurations. If cosmic strings exist, they could warp space around them and influence the motion of matter over large distances. In principle, a network of such defects might leave characteristic imprints on the distribution of galaxies, perhaps seeding unusual filaments or arcs. Current observations place strong limits on the allowed properties of cosmic strings, and no definitive evidence for them has been found. Yet they remain an example of how the largest structures could, in principle, encode information about physics at energies far beyond those accessible in particle accelerators. Another line of thought links the unusually large features to conditions before or during the inflationary phase that is thought to precede the hot Big Bang. Inflation is typically modeled as a period of exponential expansion driven by a scalar field with a simple potential. Small quantum fluctuations in that field are stretched to cosmic scales and become the seeds of later structure. If, however, the inflating region experiences variations, interruptions, or interactions with other fields, it could generate non-standard patterns in the primordial fluctuations. This might include additional large-scale modes or correlations that later show up as unusual structures in the galaxy distribution. The detailed connection between such early events and specific later features is complex and highly model-dependent, but the basic idea is that the largest patterns in the cosmic web are in some sense amplified shadows of whatever shaped the universe just before it became hot and dense. In perhaps the most adventurous proposals, the presence of structures that seem too large for the standard picture is interpreted as a hint that the observable universe is part of a sequence of cosmic epochs, and that some of its large-scale organization may be inherited from a previous phase. In these cyclic or conformal models, the Big Bang is not an absolute beginning, but a transitional event between aeons. Regularities that extend across huge distances could then be seen as traces of patterns laid down before the current expansion began. At present, these interpretations remain speculative, and the data do not demand them. Conventional explanations involving a rare but not impossible fluctuation in an otherwise standard universe or unresolved systematics in the way structures are identified are still viable. Yet the mere possibility that the largest arrangements of galaxies might carry information about conditions preceding the familiar hot phase illustrates how large-scale structure acts as a bridge between observation and ideas about what, if anything, came before the Big Bang. Each new discovery of an unusually extended or geometric feature, therefore, does more than add a point to a catalog. It nudges the conversation about cosmic origins, suggesting that if there is a deeper prehistory, it might be written not only in the faint light of the background radiation, but also in the grand architecture of the galaxy distribution itself. Modern cosmology does not describe the universe as made mainly of the familiar matter that can be seen directly. Observations of the cosmic microwave background of galaxy motions and of the large-scale structure all point to a picture in which ordinary matter forms only a modest fraction of the total cosmic content. The rest is divided between two components that are invisible but whose gravitational effects are evident. One of them, called dark matter, behaves like a pressureless substance that clusters and forms the scaffolding of the cosmic web. The other, called dark energy, acts more like a smooth energy density associated with space itself, driving the expansion of the universe to accelerate. Together, they shape the history and fate of cosmic evolution, yet their true nature remains unknown. Evidence for dark matter accumulates through several independent lines. The outer parts of spiral galaxies rotate faster than can be accounted for by the visible stars and gas alone. Clusters of galaxies contain hot gas, whose temperature and distribution reveal that there must be far more mass than is seen in light. Gravitational lensing, the bending of light from distant sources as it passes near massive structures, often indicates mass concentrations that outstrip the luminous content. Numerical simulations of structure formation also require an unseen component if they are to reproduce the observed distribution of galaxies and clusters. In all of these contexts, dark matter acts as if it were made of particles that interact very weakly with radiation and ordinary matter, but respond to gravity in the usual way. For decades, laboratory experiments have searched for such particles, looking for rare collisions in underground detectors or indirect signals from their possible annihilation. So far, no convincing detection has been made, and the allowed region of parameter space has narrowed. This absence of direct evidence leaves room for alternative ideas, such as modifications of gravity on certain scales, but the success of dark matter in reproducing a wide range of cosmic phenomena keeps it as a central ingredient in the Standard Model. Dark energy enters the picture more recently. In the late 1990s, measurements of distant supernovae used as standard candles indicate that the expansion of the universe is not slowing down under gravity, as once expected, but speeding up. Combined with cosmic microwave background data and large-scale structure surveys, these observations point to a universe in which roughly 2/3 of the total energy density resides in a component with negative effective pressure. In the simplest interpretation, this component is a cosmological constant, a fixed energy associated with the vacuum of space. When included in the equations of general relativity, a cosmological constant produces repulsive gravity on large scales, causing the expansion rate to increase over time. A model that combines cold, dark matter with a cosmological constant and a nearly scale-free spectrum of primordial fluctuations fits a wide range of data and becomes the standard framework for cosmology. This model, however, raises profound questions. The value of the cosmological constant required to match observations is extremely small compared to naive estimates from quantum field theory, which predict a vacuum energy many orders of magnitude larger. Why the actual value is so tiny and why it becomes dynamically important only in the relatively recent universe are open problems. These puzzles motivate the exploration of alternatives in which dark energy is not a pure constant, but evolves over time perhaps as a field that slowly changes its value. Such models predict subtle departures from the expansion history of the simple cosmological constant case. To test these possibilities, cosmologists undertake increasingly precise measurements of how the expansion rate changes with redshift. One powerful method uses baryon acoustic oscillations as a standard ruler. The preferred scale imprinted in the galaxy distribution by early sound waves in the primordial plasma can be measured at different epochs, providing information about how distances and expansion have evolved. Large spectroscopic surveys map millions of galaxies and quasars to trace this ruler across cosmic time. Among these efforts, a project known as the Dark Energy Spectroscopic Instrument is designed specifically to chart the three-dimensional distribution of matter over a wide range of redshifts with high detail. Its strategy combines observations of bright nearby galaxies, more distant emission line galaxies, and even more remote quasars, building a layered picture of structure from relatively recent times, back to when the universe is only a few billion years old. As data accumulate, analysts compare the observed clustering and distance relationships with those predicted by the standard model. Early results suggest that while the overall picture of an accelerating universe is confirmed, there may be mild tensions in the exact form of the acceleration. Some reconstructions of the dark energy equation of state, a parameter that captures how its pressure relates to its density, hint that it might deviate slightly from the constant value associated with a pure cosmological constant. There are indications in some analyses that the influence of dark energy may have been stronger or weaker at earlier times than the simplest model assumes, or that it could be evolving slowly. These hints are not definitive. Systematic uncertainties in the data choices, in the statistical methods, and the combination of different probes all affect the inferred behavior of dark energy. Some teams find that a constant dark energy remains an adequate fit within current errors. Nevertheless, the possibility of evolution remains open and ongoing surveys are designed to sharpen the picture. Parallel to this, other tensions emerge. Local measurements of the Hubble constant the current expansion rate using distance ladders based on nearby objects sometimes give values higher than those inferred from fitting the cosmic microwave background with the standard model. Measurements of the present day, clumpiness of matter from weak lensing and galaxy clustering occasionally suggest less growth of structure than expected. Taken together, these discrepancies suggest that the simple model might be missing a piece, whether in the behavior of dark energy, the properties of dark matter, or the law of gravity itself. In this context, an evolving dark energy becomes a natural candidate for explanation. If the repulsive effect that drives acceleration changes over time, it could alter both the distance scale to the cosmic microwave background and the growth of structure in ways that reduce the tensions. Various theoretical models implement such behavior through scalar fields-coupled components or modifications of the gravitational action. Each produces a characteristic signature in the expansion history and in the pattern of cosmic structures. Observationally distinguishing between these possibilities requires very precise measurements and careful control of systematic errors. For the moment, many scenarios remain viable. Beyond the immediate task of resolving current tensions, the nature of dark energy has deep implications for the future of the universe. If it is a true cosmological constant, its influence will continue to grow as matter becomes more diluted by expansion. Galaxies not gravitationally bound to one another will recede ever faster, and the observable universe will gradually empty of accessible structures. Stars will exhaust their fuel, and in the far future, the cosmos will approach a cold, sparse state. If dark energy weakens over time, a different fate is possible. The acceleration could slow halt or even reverse, allowing gravity to dominate again on large scales. In some models, this leads to a future recollapse, a big crunch, in which the universe contracts toward high density. In others, the expansion continues, but at a gentler, decelerating pace. There are also models in which dark energy becomes stronger, driving an ever more rapid expansion that eventually tears apart bound structures in a scenario sometimes called a Big Rip. These possibilities are not simply stories about the distant future. They also connect back to the question of what might have happened before the Big Bang. In cyclic cosmologies, for example, a period of accelerated expansion driven by dark energy can smooth and dilute the universe before a subsequent contraction and bounce. The detailed behavior of dark energy thus determines whether cycles can occur and what properties they have. In models where transient bursts or multiple singular events punctuate cosmic history, the effective strength and decay of the driving field resemble a time-varying dark energy. In this way, present-day measurements of the expansion do not only inform the fate of the current universe, they also constrain the plausibility of scenarios in which the Big Bang is not a unique beginning, but one node in a longer chain of events. For now, dark energy remains a phenomenological term, a label for a set of observed effects, rather than a fully understood substance or mechanism. Its presence is inferred with high confidence, but its essence is unknown. Every new survey that maps galaxies, quasars, and the cosmic web with greater precision adds to the evidence and refines the allowed space of models. At the same time, small discrepancies in the data keep alive the possibility that something more subtle is at work. Whether the answer lies in a simple constant, a slowly rolling field, an interaction with dark matter, or a deeper modification of gravity itself, the outcome will bear directly on how cosmologists think about the boundary at the Big Bang. A universe whose acceleration is driven by a stable vacuum energy might suggest a different kind of origin than one whose acceleration is only temporary, the fading after effect of a past transition. In this sense, the invisible push that shapes the large-scale expansion of the cosmos today is linked to the question of what, if anything, existed before the bright beginning, that current observations so clearly reveal, but do not fully explain. The standard narrative of cosmology rests on a single great event. In this story, the universe begins in a hot, dense state, then expands and cools in a generally smooth way, with no further singular interruptions. Dark matter and dark energy are introduced as additional components to explain how structures grow and how the expansion accelerates. Yet, there are alternative frameworks in which the universe does not rely on a single primordial explosion and two mysterious ingredients. Instead, the expansion history and the formation of structure arise from a sequence of more localized events that resemble miniature beginnings. In these speculative models, the cosmos is not created once, but is repeatedly nudged by brief episodes of intense activity. One such approach imagines that the fabric of space-time can host transient singularities that appear, act, and vanish. Rather than a single Big Bang, there are many small bangs. Each event injects energy and matter throughout space, changing the expansion rate and leaving behind new material from which structures can form. Between these events, the universe follows the familiar rules of general relativity with ordinary matter and radiation coasting along with no need for a separate persistent dark energy. The novelty lies in the character of the singularities. They are not permanent boundaries where time begins or ends, but fleeting mathematical spikes that briefly dominate the equations and then disappear. This idea has a distant echo in the steady-state hypothesis proposed in the mid-20th century, which attempted to reconcile an expanding universe with an eternal, unchanging large-scale appearance. In that older model, new matter is continuously created to keep the average density constant as space expands. The steady-state picture ultimately fails under observational scrutiny, in part because it requires ongoing creation of matter in a way that conflicts with energy conservation and because it does not account for the observed evolution of galaxies and the cosmic microwave background. The modern transient singularity scenarios differ in important ways. They do not posit continuous creation. Instead, they introduce brief episodes of mass energy injection that occur so rapidly that in the limit they occupy no finite duration. In mathematical terms, the fields that describe gravity and matter acquire terms that behave like impulses. For an instant, they alter the energy content and pressure of the universe, and then they are gone. In such a framework, the Big Bang itself is simply the earliest of these events that can be meaningfully described, not necessarily the first in an absolute sense. It is a particularly strong or significant impulse that sets the initial hot conditions of the observable universe. Later, weaker impulses could occur at much lower energy scales, adjusting the overall expansion rate or providing extra material in a way that imitates the effect of dark energy and dark matter. In some formulations, the negative pressure associated with these singularities produces a temporary acceleration of expansion, much as dark energy does in the standard model. At the same time, the uniform injection of matter can mimic the role of dark matter in seeding structure. In this way, a single mathematical mechanism attempts to account for several phenomena that are otherwise attributed to separate unseen components. To make such models concrete, theorists write modified versions of the Friedmann equations that govern the expansion of the universe. They include terms that represent sudden changes in the energy density or pressure at specific times. Between these times, the universe behaves like a conventional cosmological model with matter and radiation. At each impulse, the scale factor, which measures the size of the universe or its derivatives, may undergo sharp changes. The challenge is to do this without violating basic conservation laws or introducing contradictions with well-tested physics. Some proposals argue that because the singularities are of measure zero in time, the usual conservation rules can be preserved in a generalized sense. The bursts occur so briefly that in the limit they do not contribute a finite integral over time, even though they leave a discrete change in the state of the universe. This is a subtle argument, and not all physicists find it compelling, but it illustrates how mathematical ingenuity is used to explore possible extensions of standard cosmology. If multiple small bangs have occurred, they should leave traces. One possible signature lies in the relationship between redshift and distance. In a universe dominated by a smooth, constant dark energy, this relationship follows a specific curve. If instead the expansion rate has changed in a step-like manner, at certain epochs, the curve may exhibit small discontinuities or kinks. Distant galaxies and quasars at similar redshifts might fall into slightly different distance regimes than expected from a smooth model, depending on whether their light has traveled through the cosmos before or after a particular burst. Large surveys that measure precise distances and redshifts for millions of objects could, in principle, detect such subtle features. Cosmologists therefore examine the data for signs of departures from a smooth expansion history. So far, no clear evidence of discrete jumps has emerged, but the precision of the measurements is still improving, and the interpretation is complex. Another possible imprint is in the statistics of large-scale structure. If bursts of creation add matter uniformly throughout space at specific times, they alter the growth of fluctuations. Structures that have already begun to form may suddenly find themselves embedded in a denser overall background, changing the rate at which gravity pulls matter together. This could modify the abundance of galaxy clusters, the height of peaks in the matter-power spectrum, or the scale at which homogeneity is reached. High-precision measurements of clustering such as those provided by spectroscopic and weak lensing surveys therefore act as tests of such models. Any significant discrepancy between the predicted and observed pattern of structure could either constrain or support the idea of multiple singular events. In practice, the current data are more naturally described by smooth models with continuous dark energy, but the possibility of more complex histories remains open within the uncertainties. The cosmic microwave background also provides a check. The background radiation emerges from a time when the universe is still relatively young. A burst occurring long after recombination would not directly affect the conditions at that epoch, but could change the apparent distances to the background surface and the way structures between that surface and the observer lens the radiation. This would alter the angular scale of features in the background map and the statistical properties of lensing-induced distortions. Precise measurements of the background power spectrum and its lensing therefore limit how dramatic any late-time singular impulses could be. The fact that the observed background agrees well with a simple model that has smooth, dark energy suggests that if multiple bursts exist, they must be subtle or confined to early periods that are less accessible to observation. Despite these constraints, the appeal of multiple bang models lies in their conceptual unification. Instead of postulating separate unknown substances for dark matter and dark energy, they attempt to derive the observed behavior from a repeated underlying process. They also open a way to think about the Big Bang itself as one episode in a series rather than an isolated beginning. In some versions, the bursts may be associated with transitions in underlying fields, perhaps linked to changes in vacuum state or symmetry-breaking events. In others, they are more abstract mathematical constructs. Either way, they suggest that the history of the universe might be punctuated by short, intense phases that are invisible to direct observation but evident in their integrated effects. It is important to emphasize that such ideas remain far from the mainstream. The standard model with cold dark matter and a cosmological constant continues to match most data with fewer assumptions and parameters. Multiple bang scenarios must not only reproduce the successes of the standard picture, but also explain why their extra complexity is justified. Unless they solve specific tensions or make distinctive predictions that are confirmed, they remain speculative exercises. Still, their existence highlights a key feature of cosmology as a science at the edge of knowledge. Observers measure light and matter distributions within the observable universe. Theorists construct models that fit those measurements and extrapolate them to unseen realms. When the extrapolation reaches back toward the Big Bang, the path becomes less constrained. It is in this zone that the idea of many small bangs of transient singularities appearing and vanishing across cosmic time finds room to be considered. Whether or not it ultimately describes reality, it broadens the space of possibilities for what the early universe could have been and for how the apparent beginning might connect to a deeper, perhaps more complex prehistory. When the Big Bang is treated not as an absolute beginning, but as a boundary where known physics reaches its limit, it becomes natural to ask whether this boundary might connect two different phases of cosmic history. In that view, the early hot dense state is not the first chapter of existence, but a transition between one regime and another. Several theoretical frameworks explore this possibility, each extending the idea of a universe with a single origin into a wider story of cycles, bounces, or preceding worlds. They differ in detail, but share a common goal to replace the singular starting point of classical cosmology with a more complete account in which time continues in some form beyond what is usually called the beginning. One such proposal is the conformal cyclic cosmology, put forward by Roger Penrose and collaborators. In this picture, the universe evolves over an extremely long time scale toward a state in which all matter decays, black holes evaporate through Hawking radiation, and only massless particles, such as photons and perhaps very light fields, remain. As the universe expands and cools, the characteristic mass scales that distinguish objects gradually lose their importance. In the far future, with no massive particles and no bound structures, the geometry of space-time can be rescaled without changing the behavior of the remaining fields because the physics of massless particles is insensitive to overall scale. In conformal cyclic cosmology, this nearly empty cold future universe is then mapped through a mathematical operation known as a conformal transformation onto the hot dense state of a new Big Bang. In other words, the infinite future of one cosmic aeon is linked to the beginning of the next. The boundary between them is not a singularity in the usual sense, but a surface across which the geometry is smoothly rescaled. Each aeon has its own history of galaxy formation, black hole growth, and eventual decay, and the present universe is simply one stage in an endless succession. If this picture is correct, events in a previous aeon could leave subtle imprints in the earliest observable stages of the current one. Penrose has suggested that certain features in the cosmic microwave background, such as concentric circular regions with slightly different temperature variants, might be relics of gravitational disturbances from the past aeon, for example, the final merges and evaporation of supermassive black holes. These disturbances propagating as gravitational waves could cross the conformal boundary and produce low-contrast rings in the hot plasma that later becomes the background radiation. Analyses along these lines have claimed to find such patterns, while other independent studies argue that the data are consistent with random fluctuations, once statistical uncertainties and selection effects are properly taken into account. The debate illustrates the difficulty of extracting firm conclusions from a single sky, where every possible pattern is unique and the line between signal and coincidence is thin. At present, conformal cyclic cosmology remains a mathematically intriguing and physically speculative framework, one that has not yet secured clear observational support, but that offers a concrete way to think of the Big Bang as the inheritance of a previous universe, rather than its absolute birth. A different route to extending cosmic history beyond the classical singularity comes from attempts to merge general relativity with quantum ideas. In loop quantum gravity space is treated as having a discrete structure at the smallest scales built from fundamental loops or quanta of geometry. When this approach is applied to cosmology in what is known as loop quantum cosmology, the classical singularity is replaced by a bounce. As the universe contracts toward high-density quantum effects, generate a repulsive component in the effective gravitational dynamics, preventing the density from diverging. The contraction slow stops at a finite maximum density and then reverses into expansion. In this scenario, the Big Bang is not a point where time begins, but the moment of reversal between a preceding contracting phase and the current expanding phase. The universe has a prehistory in which structures might form, evolve, and perhaps be erased or transformed as the bounce is approached. Because the bounce takes place under conditions of extreme density and curvature, most detailed information about the contracting phase may be lost, but certain global features, such as the overall pattern of primordial fluctuations, could carry traces of the pre-bounce dynamics. Loop quantum cosmology predicts specific modifications to the spectrum of primordial perturbations that seed structures, especially on very large scales. These might appear as small deviations from the nearly scale-invariant pattern expected from standard inflation, perhaps including a suppression of power at the largest angles in the cosmic microwave background or distinctive forms of non-Gaussianity. Current data are not yet precise enough or sufficiently free of systematic uncertainties to decisively confirm or rule out these subtle effects. Still, the framework shows how a theory of quantum gravity could, in principle, remove the singular beginning and replace it with a bounce that extends time beyond the Big Bang without invoking exotic new matter components. Yet, another class of models envisions a cosmos embedded in a higher dimensional setting where our visible universe resides on a three-dimensional surface or brane within a larger space. In some of these brane world scenarios associated with ideas from string theory, the hot Big Bang is interpreted as the result of a collision between two such branes. Before the collision, the branes approach each other in a higher dimensional bulk. The energy of their motion is converted into heat and particles on the branes when they make contact, producing a hot, dense state that looks from the inside like a Big Bang. Under certain conditions, this process can occur repeatedly, with the branes oscillating and colliding in a series of cycles. In the ekpyrotic and cyclic models based on this idea, Each cycle includes a period of slow contraction that smooths and flattens the universe, followed by a bounce associated with the brain collision, and then a long phase of expansion, not unlike the standard cosmological story. The advantage of these models is that they offer an alternative to inflation for explaining the observed homogeneity and flatness of the universe. The slow anisotropy damping contraction phase acts as a preparatory stage that erases irregularities, so that the new expansion emerges from a nearly uniform high-density state. As in other cyclic pictures, there is no unique origin. Instead, cycles extend indefinitely into the past and future. Observationally, these brain world scenarios can be tested by looking at the detailed properties of primordial fluctuations. For example, the spectrum of gravitational waves produced in ekpyrotic contraction differs sharply from that predicted by many inflationary models. While standard inflation often generates a nearly scale-invariant spectrum of tensor modes, ekpyrotic models tend to produce far fewer primordial gravitational waves on observable scales. Searches for the imprint of such waves in the polarization of the cosmic microwave background therefore act as a discriminant. So far, no clear detection of primordial gravitational waves has been made, which leaves room for both inflationary models with low tensor amplitudes and certain cyclic alternatives. The challenge is that many different early universe scenarios can be tuned to match existing data at the level of precision currently available. All of these frameworks, from conformal cycles through quantum bounces to brain collisions, share a structural resemblance. They avoid a true beginning by extending time on one or both sides of the hot phase. They also raise questions about memory. How much information about a previous cycle or contracting phase can pass through a bounce or conformal boundary into the next aeon? Does the arrangement of structures on the largest scales or the pattern of tiny fluctuations in the background radiation preserve any recognizable imprint of a pre-Big Bang era? Some models predict that only very coarse features, such as the overall statistical distribution of perturbations, survive. Others suggest that more specific signatures, like particular alignments or non-random patterns, might be observable. Distinguishing these possibilities requires both careful theoretical work and extremely precise measurements. At present, no single model of a pre-Big Bang universe stands out as preferred by data. Classical Big Bang cosmology with inflation remains the simplest effective description of what is observed from the earliest accessible times onward. Yet, the existence of consistent alternative frameworks shows that once the singularity is approached, the space of viable stories widens. The same background radiation and large-scale structure that support the idea of a hot beginning can also be interpreted in principle as the aftermath of a bounce, a collision, or the end of a previous cycle. In this way, the question of what came before the Big Bang is not dismissed as meaningless, but reformulated as a problem of how to connect different phases of cosmic evolution across extreme boundaries, and of how traces of a prior world might remain encoded in the one that is visible today. Up to this point, the discussion of what may have preceded the Big Bang has rested on a broadly classical picture of time. In that picture, time is a coordinate labeled in cosmology by a cosmic time parameter that measures the interval since the onset of expansion. The Big Bang singularity sits at the lower end of this coordinate. It is the place where the mathematical description says that the scale factor of the universe goes to zero, and the density and temperature diverge. Within general relativity, when applied to a homogeneous and isotropic universe, this singularity is not a point within time, but the edge of the time axis itself. Asking what happened before that edge is in this framework like asking for values of the coordinate that simply do not exist. There is no earlier stage, just as there is no point on a half-line before its endpoint. In this sense, classical relativity encourages the view that time begins at the Big Bang, and that the phrase before the Big Bang refers to a region that is outside the domain of applicability of the theory. However, this classical view sits uneasily with the quantum description of matter and fields. Quantum field theory is constructed on a fixed space-time background with time treated as an external parameter. The fields evolve with time, and probabilities are defined by amplitudes that depend on temporal evolution. When gravity becomes strong enough that the geometry of space-time itself must be treated quantum mechanically, this split between a classical time coordinate and quantum fields becomes problematic. One can no longer assume that there is a fixed background on which events unfold. Instead, the geometry is dynamic and subject to quantum uncertainty. In attempts to quantize gravity, time may appear not as an independent parameter, but as an emergent quantity, arising from relations between different degrees of freedom. This conceptual shift changes how one thinks about the Big Bang. The singularity in classical relativity marks the breakdown of the classical description, but a quantum theory could, in principle, continue past that point in a different language. In canonical approaches to quantum gravity, there are formulations in which the fundamental equation does not contain time explicitly. The state of the universe is described by a wave functional that encodes all possible configurations of geometry and matter. What appears to be time evolution arises from correlations within this state, as some degrees of freedom play the role of clocks relative to others. In such a setting, the question of what happened before a particular classical configuration becomes a question about the structure of the quantum state. The Big Bang is then not an absolute temporal origin, but a region in configuration space where the classical variables describing the scale of the universe take small values. The notion of before may correspond to other branches or regions of the wave functional rather than to earlier points on a classical timeline. This is a subtle and abstract way of thinking, far removed from everyday intuition, but it illustrates how the concept of time itself becomes fluid when quantum gravity is considered. Another perspective comes from path integral approaches in which one computes amplitudes by summing over histories. In such methods, the probability for the universe to have a particular configuration today is obtained by integrating over all possible four-dimensional geometries and field configurations that match that configuration on a boundary surface. In this language, one can attempt to specify the boundary conditions of the universe not by positing a singular starting point, but by imposing a regularity condition on the allowed geometries. One influential idea along these lines is the proposal that the universe has no initial boundary in a classical sense. Instead, the quantum history is dominated by configurations in which near what would classically be the Big Bang time behaves more like a spatial direction. The geometry is smooth and finite, with no edge where conditions must be arbitrarily fixed. The familiar distinction between time and space emerges only after this early region, when the geometry takes on a form that can be approximated by a classical expanding universe. In this view, there is no literal before the Big Bang, because near the origin, the concept of time as an ordering of events ceases to have its usual meaning. Instead, there is a rounded region in the space of geometries without a sharp boundary. The hot, dense state is then not an imposed initial condition, but the natural outcome of the most probable quantum histories that satisfy the regularity condition. These formulations do not provide a simple narrative about a previous phase in time, but they do replace the idea of creation from nothing with a more nuanced concept. The apparent beginning is a region where the classical description fails, and where a quantum description reveals a different kind of structure. What seems like nothing, in the sense of an absence of space-time and matter, is replaced by a highly non-classical state of geometry and fields. Whether that state is best described as a prior phase, a timeless configuration, or something else entirely, depends on the details of the theory. In all cases, the vocabulary of before and after which works well in everyday contexts becomes inadequate at the boundary where time itself is emergent. Beyond these formal constructions, there are phenomenological reasons to question whether time really has an absolute origin. The near-scale invariance of primordial fluctuations, the apparent flatness and homogeneity of the universe, and the presence of a horizon in the cosmic microwave background all suggest that some process acted before the hot Big Bang phase to set up initial conditions. Inflation, with its brief period of accelerated expansion, is one such process. It can be embedded within a classical spacetime that begins at a singularity, but it can also be extended into models where the inflating region arises from a prior phase. For example, in some scenarios, inflation is eternal to the past and future in a probabilistic sense, with new inflating regions continually budding off from older ones. In others, inflation is preceded by a contracting phase that smooths the universe before a bounce. In each case, time extends beyond the naive Big Bang, even if the details remain speculative. The Big Bang becomes a transition between regimes, not the first moment of existence. The notion of time may also be richer than a simple one-dimensional parameter. In some theories, there are multiple fields that can serve as internal clocks, each defining its own measure of progression. Near a quantum gravitational regime, these clocks may disagree or become ill-defined. Only at lower energies, when the universe is large and curvature is small, do they converge on a single, effective time variable that can be used in cosmology. This suggests that asking what happened before the Big Bang without specifying which clock one is using may be an ill-posed question. The appropriate description could involve a phase where no single global time variable exists, and only local or relational notions of temporal ordering make sense. Such considerations are at the frontier of theoretical physics and are not yet anchored in empirical tests, but they form part of the effort to understand what the singularity in classical models is telling us. Observationally, the question is how any of these ideas can be confronted with data. Since direct access to the Planck scale regime is impossible, with current technology, cosmologists look for subtle signatures that quantum gravitational effects might leave in the primordial universe. These include specific deviations from the simplest inflationary predictions, such as small departures from a perfect power law in the spectrum of primordial perturbations, distinctive patterns of non-Gaussian correlations, or particular forms of primordial gravitational waves. Measurements of the cosmic microwave background, large-scale structure, and perhaps future observations of very low-frequency gravitational waves become the testing ground. If certain predicted features are found, they could point toward one class of models over another, offering indirect insight into the nature of time near the Big Bang. If, on the other hand, data continue to support the simplest models without such signatures, more elaborate theories may be constrained or forced to adjust. Regardless of the outcome, the conceptual shift introduced by these investigations is significant. The Big Bang is no longer treated only as a time at which things begin, but as a region where classical notions of time and causality change character. Whether that region connects to a contracting phase, another aeon, or a timeless quantum state, it is unlikely to be well described by the familiar picture of a singular point emerging from nothing. The phrase, "before the Big Bang," may still be used as a shorthand, but its meaning depends on the theoretical framework. In some models, there is a genuine earlier phase with its own history. In others, the notion of earlier dissolves, replaced by a more abstract structure. Even in cases where the concept of before is judged meaningless, this judgment rests not on a simple declaration, but on a detailed understanding of how time arises from deeper laws. In this sense, questioning time itself does not eliminate the mystery of origins. It rearranges it. The universe can no longer be pictured simply as a sequence of events starting from a singular instant. Instead, it may be rooted in a more intricate foundation, in which space-time matter and the flow of moments are all emergent aspects of a quantum gravitational reality. The Big Bang, as seen in the light of the cosmic microwave background and the distribution of galaxies, marks the beginning of the classical expanding universe. Beyond that, in mathematical structures that are still being clarified, there may be layers in which the distinction between something and nothing, and between before and after, is far less clear. It is in those layers that a precise answer to what existed before the Big Bang, if such an answer exists, would need to be found. Across all the observations and theories that have been considered a theme, emerges the universe appears to carry memory. Not memory in the conscious sense, but a physical record encoded in light matter and the geometry of space-time. The cosmic microwave background preserves conditions from a time when the universe is only a few 100,000 years old. The distribution of galaxies and the largest structures reflects billions of years of gravitational growth. The current rate of expansion and any evolution of dark energy embody the integrated influence of whatever fields and processes have acted over cosmic history. Even the absence or presence of subtle signatures in the statistics of primordial fluctuations can be read as traces of the earliest accessible moments. The question of what, if anything, existed before the Big Bang becomes, in this context, a question about how far this physical memory extends and how clearly it can be decoded. The firmest part of the record begins after the hot dense phase is well underway. Nuclear reactions in the early fireball set the relative abundances of light elements such as hydrogen, helium, and a small amount of lithium. These abundances are measured in ancient gas clouds and old stars and match calculations based on a hot beginning. The cosmic microwave background provides a direct image of the universe when it first becomes transparent. Its overall uniformity and detailed pattern of small anisotropies are consistent with a period of rapid inflation, followed by a gradual expansion dominated first by radiation, then by matter, and finally by dark energy. Large-scale galaxy surveys and weak lensing maps show how structures grow from those initial fluctuations. Taken together, these observations form a coherent story from very early times through to the present, with relatively few adjustable parameters. Most cosmologists regard this as a strong indication that the broad outline of the hot Big Bang model is correct. Yet within this overall coherence, small discrepancies and unexpected features act as possible hints that the model is incomplete. The cosmic microwave background might display anomalies on the largest angular scales, such as unusually low power or curious alignments. High redshift observations reveal early galaxies that appear more massive, more chemically evolved, or more numerous than simple models predict for such young epochs. The discovery of extremely large structures like the Big Ring and the Giant Arc, and other vast walls and filaments, pushes the expected scale at which homogeneity sets in. Measurements of the current expansion rate and the growth of structure sometimes show mild tensions when compared with the parameters inferred from the microwave background. Surveys of baryon acoustic oscillations and other distance indicators hint in some analyses that dark energy may not be perfectly constant. Each of these issues can in principle be attributed to statistical chance, to underestimated uncertainties, or to aspects of astrophysics that are not yet fully captured in models. None demands a radical revision of cosmology on its own. However, the fact that they occur in several different areas lends them extra interest. One way to view these anomalies is as noise that will eventually average out. Another is to see them as potential traces of physics that operated under conditions no longer directly accessible, possibly including phases that precede the classical Big Bang. If certain patterns in the cosmic microwave background are real and not artifacts, they could reflect exotic processes in the earliest moments when quantum gravity effects are important, or even disturbances carried over from a prior aeon in a cyclic model. If early galaxies are consistently more mature than expected, that might mean that initial conditions include more small-scale power than standard inflationary scenarios allow, or that dark matter behaves differently in the young universe, or that star formation under pristine conditions is more efficient than local analogs suggest. The largest structures might in turn hint that the initial fluctuation field contains correlations on scales that are not easily generated by simple inflation. A change in dark energy could imply that the vacuum is not a fixed background property, but at least partly the residue of a field that evolves across cosmic epochs. In aggregate, these are suggestions rather than conclusions, but each points in the same general direction. The early universe may be more complex than the minimal model assumes, and some of that complexity could extend into a pre-Big Bang domain. If the universe does remember anything from before the hot phase, the memory is likely to be highly compressed and filtered. Extreme conditions near the classical singularity or during a bounce or brain collision would erase much of the detailed structure of any preceding state. Only robust, large-scale features such as the overall distribution of perturbation amplitudes, certain symmetry properties, or the presence of particular relic fields might survive. In conformal, cyclic cosmology, the remnants of black hole mergers and decay in a previous aeon could translate into subtle rings in the microwave background. in loop quantum cosmology. The pre-bounce dynamics might leave a characteristic imprint on the largest scale fluctuations. In brain-based cyclic models, the physics of the contraction and collision could set the shape and non-Gaussianity of primordial perturbations. In multiple bang scenarios, a sequence of transient singularities could produce a step-like expansion history and affect how structures grow. Each class of model implies a different way in which the universe could carry forward at least a fragment of its earlier conditions. Observationally, the challenge is to identify signals that are both distinctive and robust. Distinctive signals are those that are not easily mimicked by mundane effects, such as instrument noise, foreground contamination, or conventional astrophysical processes. Robust signals are those that persist across different data sets, different analysis methods, and different teams. The search for such signals is ongoing. Large collaborations reanalyze microwave background maps, improving foreground subtraction and calibration. Deep surveys with the James Webb Space Telescope and other observatories refine the census of early galaxies, their luminosities, sizes, and chemical compositions. Spectroscopic instruments map baryon acoustic oscillations and the three-dimensional clustering of matter over ever wider volumes. Weak lensing programs measure the distribution of dark matter with increasing precision. In each case, small deviations from the simplest models are scrutinized for systematic explanations before being considered as evidence for new physics. The process is slow, incremental, and often frustrating, but it is precisely through such careful work that cosmic clues, if they exist, will be revealed. Theories that speculate about what existed before the Big Bang must engage with this empirical discipline. It is not enough for a model to offer a conceptually appealing story about cycles, bounces, or prior worlds. It must also reproduce the successful predictions of the standard cosmology and make at least some distinctive predictions of its own that can be tested. This demands a careful balance. If a model is too flexible, it can be made to fit any data and loses explanatory power. If it is too rigid, it is easily ruled out. Many proposed pre-Big Bang scenarios find themselves in an intermediate position where they are compatible with current observations, but not uniquely favored. This is not unexpected at an early stage. The Big Bang model itself took decades to move from a speculative idea to a widely accepted framework guided by successive discoveries such as the cosmic microwave background and the detailed mapping of large-scale structure. A similar progression, if it occurs for any pre-Big Bang theory, will likely require new observational breakthroughs and perhaps a deeper understanding of quantum gravity. There is also the possibility that the empirical record simply stops at a certain point. The cosmic microwave background already marks a surface beyond which direct electromagnetic observation cannot reach because earlier times are embedded in an opaque plasma. Gravitational waves, neutrinos, or other weakly interacting messengers could, in principle, carry information from earlier epochs, but detecting primordial signals of that kind at the necessary sensitivity is an enormous technical challenge. Quantum gravitational effects may be imprinted only at levels that are extremely small or confined to scales that are hard to probe. In that case, the universe may remember its earliest phases in a way that is effectively inaccessible to experiments. Theoretical models could still describe possible stories of what came before, but their relation to empirical reality would remain indirect. Cosmology would then face a boundary not only in theory, but in practice, a horizon beyond which questions about origins become more matters of consistency and elegance than of direct test. Even if that boundary exists, the endeavor to push against it is not purely abstract. Each improvement in observational precision refines the map of the early universe. Each advance in theory clarifies what is allowed and what is inconsistent. Along the way, side questions are answered. The composition of dark matter may be pinned down. The behavior of dark energy may be more tightly constrained. The history of star formation, reionization, and structure growth becomes more detailed. These are substantial gains regardless of whether they ultimately reveal a pre-Big Bang phase. They also feed back into other areas of physics informing models of particle interactions, field dynamics, and quantum gravity. In the end, the question of what existed before the Big Bang remains open. It sits at the intersection of observation theory and the conceptual foundations of time and causality. Current data trace the universe back to an early hot, dense state, and the simplest models treat that state as the beginning of time. Alternative frameworks suggest that this beginning may be only apparent a transition in a longer chain of events, or a boundary in a more general quantum description. The universe may remember earlier phases in faint patterns in the background radiation, in the arrangement of the largest structures, or in the detailed properties of primordial fluctuations. Or it may be that most of the information about any prior reality is irretrievably lost, leaving only indirect clues. As measurements improve and theories evolve, the range of viable answers will narrow, but it is unlikely that the mystery will be completely removed. The Big Bang will continue to mark the earliest clearly visible chapter in cosmic history, and the question of what, if anything, lies beyond that chapter will remain a central, quietly persistent theme in the scientific exploration of the universe. In the quiet state of the present universe, the traces of its long history surround any observer who learns how to read them. A faint microwave glow fills all of space, carrying the imprint of a time when matter and radiation are still tightly coupled. Galaxies gather into filaments and walls, revealing how small early irregularities have grown under gravity. The measured acceleration of cosmic expansion hints at an unknown influence, while the unseen mass that guides galaxy motions suggests a hidden component woven through the cosmos. Together, these elements form a record that stretches back almost to the hot beginning. Beyond that, the story becomes less clear. Classical general relativity points to a boundary where its own equations fail. Quantum ideas suggest that time and space may emerge from a deeper level of description, one in which the familiar distinction between before and after is not yet defined. Some theories imagine cycles of universes where the end of one cosmic era becomes the beginning of the next. Others describe bounces, collisions, or phases in which time behaves differently. All remain possibilities tied to hints in data and to mathematical structures that are still being explored. In this landscape of ideas, the Big Bang is not a solved origin, but a marker. It is the earliest chapter that can be read with confidence and at the same time a signpost pointing toward questions that are not yet answered. The evidence so far suggests a universe that remembers much of its past, but may conceal its deepest beginnings behind layers of extreme conditions and quantum behavior. Future instruments and theories will sharpen what can be seen and described. Whether they reveal a clear picture of a pre-Big Bang reality or only narrow the range of what is plausible, they will refine the understanding of how a cosmos like this one comes to be. For now, the question of what existed before the Big Bang remains open, a quiet presence at the edge of knowledge, inviting continued patient inquiry.